Let's look at the idea of completing the square, which follows on nicely, of course, from quadratic equations. So here's a quadratic, which, yes, okay, I know we could factorise this and come up with a solution, but let's use as an example of the technique of completing the square, which you may recall. It's one of those things where we just go through the same process each time. The first thing we do is, well, let's move the constant to the other side. So the 7 goes to the other side. Then once we've done that, we add half the coefficient of x squared. Now that pause is important, of course, because it's not half the coefficient of x squared, but it's half the coefficient of x squared. So the coefficient of x is 6, half the coefficient of x is 3, we add 3 squared. Why? Because on the left hand side we have completed the square. The right hand side now is a perfect square. So we can tidy that up and factorise to make our perfect square. And so we're now saying, oh, well, something squared in this case is 16, so it's either plus or minus 4. We move the negative 3 to the other side and we get our 2 possibilities. So that is, of course, the idea of completing the square. This now allows us to see where the quadratic formula comes from. So if we generalise our quadratic, ax squared plus bx plus c, first thing I'm going to do, however, is divide everything by a, because we tend to prefer monic quadratics when we're completing the square. So if I divide everything by a, so we can move the constant to the other side, add half the coefficient of x squared. So the left hand side now is a perfect square. It's x plus b on 2a all squared. The right hand side we have minus c on a plus b squared on 4a squared. So it'd be nice to make that a common denominator, and it's starting to fall into place now. So I can now say x plus b on 2a is equal to plus or minus the square root of b squared minus 4ac on 2a. We move the other term, and voila, we have our quadratic formula. So in fact that's where the formula comes from. It saves completing the square every single time. We just go, righto, we've found the pattern, let's use it to our advantage. Here's another one, x squared minus 6x plus 6. But I'm going to do it a slightly different way of thinking about it, another way of thinking about completing the square. Rather than moving the constant, you notice I haven't bothered moving the constant yet. But I know when it ends up factorising, it'll always be x and then half the coefficient of x all squared. So I know it's going to end up x minus 3 all squared. And so I simply say to myself, well, what's the constant? If I was to leave it like that and expand out, I wouldn't get 6, I'd get 9. So I can't just change the question. How do I get from 9 to 6? Well, I'll subtract 3. And what we now have is difference of 2 squares. So I could factorise that to say, oh, well, that's x minus 3 plus root 3, x minus 3 minus root 3, and we get our 2 answers. Okay, well, either it's 3 minus root 3 or 3 plus root 3. So that's an alternative approach to completing the square. That kind of comes in handy when we're dealing with complex numbers later on. Because in fact, once we know about complex numbers, every quadratic can be written then as a difference of 2 squares. At the moment we can't, because you get something like, say, well, let's think of a simple one, x squared plus 4. And you think, well, hang on, how the heck am I going to write that as a difference of 2 squares? Well, beautiful complex numbers allows us to write that as a difference of 2 squares. We shall see that obviously further down the track. Alright, that's all I got to say today. So a nice quick one. Let's spend the rest of the lesson having fun